So our final speaker, our final presenter is Richard Banati, who's from Sustainable Oil Recovery and Remediation, which thankfully they've abbreviated to SORR, and he's going to talk about their technology and some of the advances that they've got. So over to you, Richard.
Good morning. Thank you very much. I've asked for the microphone because on occasions I can get animated. I'm the chief scientist for Sustainable Oil Recovery and Remediation. And like my previous speakers, I acknowledge the traditional custodians of the land, their understanding of life and life cycle and the perpetual nature of that. That is the tacit knowledge that SORR has in practically all its activities. In fact, some of the most senior members of our team have grown up on the land, with the land, and on the waters. For them, that is truly a lived experience. Now, before I joined SORR, I worked for the Australian Nuclear Science and Technology Organization on a project of structural integrity of polymeric materials using high-dose radiation, Terra Gray, and somewhat incidentally, I came across a material that is uniquely attracting oil to a ratio that about 1,000 times its weight over its lifetime, it would extract oil and also release it undamaged, if you wish, if it's a recoverable part. It is a porous, closed, open cell structure that is, as I said, extremely robust, reusable, and quite uniquely perpetually buoyant. It would never sink to the ground. It can never be lost. Now, there is a whole lot of oleophilic, etc., technical terminology. It jars with me a little bit, but we just call it the sponge, and I will call it the sponge throughout this presentation. So let's go straight into it. It's a simplified visualization of what the material does.
Designed to protect the oceans from devastating oil spills. In the following demonstration, water is polluted with oil. The suck oil sponge is then placed on the surface of the water, where it absorbs the oil at a rapid rate. It's the first of its kind. The oil from the sponge can be extracted and reused, and the sponge can be redeployed multiple times. When tested, the suck oil sponge absorbed an unprecedented amount of crude oil, not just the first time it was used, but every time it was reused. At the end of its life cycle, the sponge can be refined into carbon black, hydrogen, and other products. This creates a circular economy where nothing ends up in landfill. But the suck oil sponge is more than just a...
I leave it there. There are a whole lot of applications. I will focus on what is decommissioning relevant. So since that sort of first scientific work in which I participated from 2019, the company has matured. It has moved out of the laboratory space. It's in commercial space. It's in upscale and growth space. And we have now the manufacturing capabilities, but retain the scientific base, customer needs driven. When I say that, one of the sort of interesting summaries that we've received from a very senior marine scientist within the oil industry, what works is not scalable, and what is scalable is not sustainable. So what is not scalable are sometimes highly sophisticated filtration, selection, and separation techniques. They can't be upscaled to the millions of liters of water that potentially has to be remediated. And with what is scalable, like sorbents, is not sustainable in terms of the environment. Another sort of sustainability criteria, one of the previous speakers has mentioned it, is of course cost. And I come to that why the material that I'm going to introduce is scalable and sustainable on these various levels. The current sort of work profile of SORR involves a number of things, mining solutions, and I probably will just focus on the oceanic solutions. Now here is essentially the core of what is a scale-free property. A scale-free property means whether that's a centimeter by a centimeter cube or a ton, the property of attracting oil, retaining it, and releasing it is retained over the scale. So it's scale-free. That's, in a way, the scientific secret. And scalable means it can be applied in a bathtub. And what you have actually seen in the movie is real time. You put it in, it pulls it out. It does so even out of mud and sand. And that is the scalability that you can do that at any volume and essentially in any geometry. That's again highlighting that what is unique in that material, and remember I said it was discovered as a usable material within high performance material testing in the nuclear sector. It can take any shape, it is long-term deployable, it is modifiable both at manufacturing level but also on site very easily. So it's a very versatile base material. It's heat resistant, so certain ISO criteria, safety criteria are covered. It's self-supporting. These things are of different relevance depending on where it's deployed. And you can see that deployment is either small or large. Again, that slide just summarized adaptability, but retaining that scale-free inherent property of the material. Okay. I've just flown in from Jeddah because there we are currently preparing the project plan for Aramco. This is the King Abdullah University that's sort of north of Jeddah, and it's specifically dedicated to environmental problems, decommissioning problems, so that is in a way our scientific anchor there. And that slide is the slide that we received from Aramco. Their operational needs, and that's not oil spills, that's just daily, ongoing, routine operational need is oily water, makes around 30%, oil-based mud cuttings, and then contaminated sand. So we can put a tick box on oily water. You have seen that was severely contaminated. I mean, high concentration, we can do it lower concentration. Sand, we have the verification. Oil-based mud, that is, of course, customer-specific, well-specific. What's the drilling liquid that's being used? So there is not a fast answer, but at least 30% of the daily ongoing operational challenges taken up by that method. So we are preparing that. We are also looking, and that is closer to the incident, accident, spill scenario, a tier 1 scenario for Petronas. A tier 1 scenario, according to the International Association, is a local spill, either as part of the decommissioning that you need a cordon sanitaire, what's that in French? Sorry, it's the safety belt around where you work, so you have either that, or if you have minor local spills, you can do that. So that's the two constraining parameters, because constraining parameters for us is just the description of listening to the customer. So the customer either has certain requirements on the material, either wants to extract PFAS, for example, then we need to modify the material, or has an established plant and wants to integrate something there. So that is the science level that's carried by a number of universities. There are 3 universities in Australia, Sydney, UTS in Sydney, and Newcastle. They do analytical, high-quality work, and then we have the plant level. That's the industry in short. So, again, the take-home message is the property here is not lost if you produce it in ton. And currently, our production capacity is 16 ton per month, and that includes the shipping and packaging on site. And 1,000 kilos is 1 million liters worth of oil. 1 liter of oil contaminates 1 million liter of water. I leave the humongous math to you, but that is, in a nutshell, what will later on percolate up as the sustainability goal. At base level, it's 1,000 times more effective. And what we do through the process engineering is try to preserve that material inherent capability. This is Fawaz Linjavi, who will represent us in in Saudi Arabia. This is in Newcastle. A major part of our activities now is the process engineering. We are out of the lab, we are in the industry. And every scenario, we've heard it earlier, is a little bit different. And so we do the process engineering there. And I put this in because, as I said, I was just there. When we turned around the window, that's the ship that was hit by the Houthis and was just about to sink. And it had a 30-mile oil slick behind it. No intervention of any kind. For the sponge, it would have been zero problem. So there was a certain urgency in the room that we need to get out and actually do it, because there's currently nothing. This is a lifeline for people who live there, the whole fishery and the regions around it. Very briefly, we have something that's called PAGE, Pollutant Adapted Gradient Extraction. That means while we produce 16 tons per month, at the point of formulation, with no loss in time or additional cost, we can modify the structure of the material, porosity, elasticity. We can essentially, in a flow, large-scale flow chemistry, create a column. We can make a column that has focus here or is a repetitive column. Why do I mention it? Because the end product could also be the mining of rare elements from the waste or from the remediated liquid material. So if you have, that's always customer specific, a particular element in mind that you wish to extract, we can formulate it at that level, at that scale-free level, and then it's scalable in terms of quantity. So that is, in essence, what underpins that circularity. We know that on first principle, the efficacy gain in that material use is 1,000-fold. All other cost-effective methods would produce for 1 million liter of waste another million liter of whatever sorbent. We are 1,000 times better on first principle, and through the process engineering, we practically don't lose that. The process engineering, as I said, is a bit the code word. We listen to the customer. What do they wish to extract in addition? And then, of course, there will be additional efficacies if they can recoup some of the valuable elements in the recovered material. There is, of course, something that lies outside our remit. That's the engineering. We have specialist applications. And here we partner, for example, with Deep Supplies, who are here at the exhibition. That's for specialist interventions around decommissioning or possibly environmental disaster scenarios. Thank you very much.